Okay. Good morning, all. In last lecture, we have started unit number 2. So already we discussed about the syllabus of unit number 2 and the objectives of unit number 2 in the last lecture. So today we will see the different isolation techniques which are used uh, to isolate logic circuits from power circuits. Okay, so why the isolation circuits are required, that we have discussed already in a last lecture. Okay, so I'll just give the introduction of the same, that is objectives of this particular unit. Then a need, normally for operating a transistor or any power device as a switch, an appropriate gate voltage or base current must be applied to the drive to drive the transistor, or maybe a MOSFET or SCR or TRI, any switching device. So to turn on the device and put into the conduction, and with a very low switch on state voltage, right? So the control voltages are normally applied to the gate to source or base to emitter of the device. The power converts generally require multiple transistors, or maybe a MOSFETs or SCRs. In last lecture, we have discussed about that. In single phase converters, you require at least maybe a 4 SCRs. In three phase converters, we required 6 SCRs and so on. So simultaneous gating signals applied to these all devices. So a proper gating circuit, or you can say drive circuit, is required in most of the uh, power converter circuits. A microprocessor based drive circuits are used, so that the SCRs or the switching devices are triggered in a proper sequence. Okay, so that is what we have discussed in the last lecture, the need of drive circuits. Okay, then most important, it is uh, what we have seen in the last lecture is uh, isolation circuits. Okay, so isolation circuits are required uh, that already we discussed in the last lecture. So all digital circuits, or you can say logic circuits or drive circuits, which works on 3 to 5 volt. For example, microprocessor, which also works on 3 to 5 volt. So these devices are maybe quite precise devices and maybe work on very low voltage and low currents, right? And we connect the output of these circuits to the power converters, or you can say maybe a power devices, right? So SCR, which works on some kilovolt voltage or level, it requires a getting signal from the microprocessor. So many times it happens the SCR, which works on very high power rating, may damage, and due to that, a large heavy current may flow through the gate towards the drive circuit. And if it happens, then definitely your drive circuits may damage permanently, right? So it happens many times. One of the device of a converter or inverter or a chopper uh, is fail, or maybe it works, maybe burnout, or sometimes maybe a breakdown. So in that situation, uh, power devices, if it breakdowns, the large current may flow through the gate of these devices, and that current may damage your logic circuit or a drive circuit. So drive circuits require isolation between power circuit and this low voltage are called as a logic circuit, right? So there are two techniques to isolate the logic circuit, or you can say gate drive circuits, from the power circuit. That is first one, pulse transformer method. There are two different techniques. There are pulse transform method and optocoupler isolation method. These are the two methods which are used to isolate the logic circuit, or you can say gate drive circuit, from the power circuit. So gate drive circuits we will see later on, but uh, before that, we will see the isolation techniques. Okay, so isolation techniques uh, that requires to isolate the uh, power circuit with gating circuits. Okay, so this is the first one, that is called pulse transform. If you see the diagram, in this diagram, we have seen a logic drive circuit. We can see in a logic drive circuit, this circuit may be a microprocessor based circuit or any other circuit which generate the triggering pulses to the power devices. Okay, so uh, we are using here a pulse transformer, right? So these are triggering pulses. Whenever triggering pulse will generate that triggering pulse, or maybe a current flow through the primary of this transformer, automatically the voltage will develop across the secondary for that time only. Whenever the logic circuit produces a triggering pulse, for that short time of period, the voltage will produce across the secondary of a pulse transformer, and this voltage which is produced across the secondary of a transformer is applied to the transistor. So what happens if suppose this transistor damage due to any reason, maybe a high temperature, or maybe a high, or maybe a voltage and current, if you apply beyond the limits, so this device definitely get damaged. And if this damage, the current can flow from VCC, RC, through the collector, then base, RB, and back to the logic circuit. But because of this pulse transformer, the large voltage which is maybe applied directly to the logic drive is blocked, right? So from this particular secondary to primary, the whatever pulses, maybe suppose device may damage, a very small current maybe flow through the logic drive circuits, and definitely your logic circuits may be protected from any kind of damage. So this is one of the method called pulse transformer. This output waveform which is shown here, this is actually a output at collector of transistor. Okay, so if you apply pulse signal, that is at the input of logic drive, only for that time the secondary voltage will develop, and which will trigger the transistor. Once transistor trigger, then current flow through transistor, transistor turns on. Your switch, maybe you can say, on. So this is the first method. By using pulse transformer, you can separate your power circuit with the logic circuit. Okay. And the second one is a optocoupler isolation method. This pulse transformer has one primary winding and can have maybe a more than one secondary winding, because in our figure only one secondary winding is shown. So this secondary winding uh, trigger only a one transistor, but you can trigger maybe a more than one transistor simultaneously by using the same triggering pulses. So pulse transformer may have maybe a two or more than two secondary windings, that is multiple secondary winding, allow simultaneous getting pulses, multiple series connected transistors or parallel connected transistor. So you can apply two, three transistor at the same time with the same triggering pulse, and it is required actually. If you see the rectifier circuit that you might have learned in second year or first year, so in that two transistors or two diodes conducts at a time, right? So that two transistors maybe conduct at the same time. uh, so sorry for interruption. So in that particular rectifier, two diodes conduct at the same time. If we replace the diodes with the SCR, because it's a control rectifier, so two SCRs can conduct at a time. So we require two triggering pulses of a same timing. So that time we use the pulse transformer with the two secondaries and so on. So that is required. In three-phase converters, we required to turn on three thyristor at a time. So we require three pulses. So that time we can select the transformer which is having the three secondary windings at a time. Okay. So this is the requirements. Uh, the transformer must have low leakage, and the rise time and fall time of pulse should be small. That is again required. Otherwise, the transformer rise time, if it is more than getting signal applied to the power devices, may be late, and maybe the turn on time of that device is decreases. So this is a requirement actually. The transformer must have very low leakage, and the rise time and fall time of pulses should be very small. Actually, whatever pulses shown here, such type of pulses definitely not getting at the secondary of transformer. The nature is something different. So that may be a type of uh, uh, ellipse, or maybe basically a exponential pulses. So definitely there will be a rise time and fall time of that pulses. So it should be a very small, otherwise the on time of the device may increases. So the duration of pulsing should not be too long to prevent the transformer goes into saturation. Again, it is very important. This is a basically disadvantage of a pulse transformer. You cannot have maybe a long gating pulses from the pulse transformer. So pulse transformer goes into the saturation. So after that, the secondary voltage, it remains on for a longer time. So this should not be uh, too long to prevent the transformer to goes into the saturation. So these are basically disadvantages of a pulse transformer method. The advantage is only one transformer is sufficient, uh, having a low cost, but the other disadvantages, that is the transformer should have very low leakage. Basically every transformer has a leakage current. So your current may be Okay, so this is the advantages and disadvantage. Advantages: the cost of pulse transformer is less. Even it is very easy to connect to the circuit for isolation purpose. But there are some disadvantages. That is, leakage current is a high. Rise time and fall time should be low. Definitely, it is also high, so that the on time of that device may decreases. So duration of pulse getting or pulses, that is output of secondary, should not be too long, otherwise your transformer goes into the saturation. So these are the disadvantages of pulse transformer method. So in place of pulse transformer method, the optocoupler isolation method is popular to isolate the power circuit with the your logic circuit, or you can say driving circuit, right? So this is a circuit uh, in front of you. So it is not change. Okay, optocoupler isolation method. I think it is still not change. The PPT in front of you. Uh, Anyone, please unmute yourself and tell me the slide, that is current slide, is optocoupler isolation method is there or not? Because I think the internet issue, so that the slides may be not okay. Now the slide in front of you is a optocoupler isolation method. Okay, so in this particular circuit, if you see that the gating signals which are applied to the LED only. Okay, gating signals are applied to the LED. There will be a photo transistor or photodiode or any other circuitry. For example, sometimes light activated SCR is also used in place of these transistors, but normally a photo transistors are preferred. Its advantages that as compared to the photodiode, the sensitivity of photo transistor is good, and photodiode has very less sensitivity. So normally photo transistor is used. So in this circuit, if you see that the MOSFET M1 is the actual component that is required a gating signal. So if you see there are okay, so now there are some internet issue, so the connection fails. Now we are at this particular optocoupler isolation method. Uh, this circuit uh, divides in two parts. This is basically a source. Actual triggering pulses generated by a drive circuit is applied to the LED, right? So whenever the pulse is available, that time the LED glows and it emits the light. That light falls on the base of uh, phototransistor, and when the light falls on phototransistor, this phototransistor conducts and current flow through the emitter of transistor. This current will flow or trigger or turn on the transistor Q2. So transistor Q2 turns on. If transistor Q1 turns on, then current flow through the transistor Q1. That time the voltage at this particular transistor collector is 0, so that transistor Q3 turns off, and that time only the triggering pulse applied to the MOSFET M1. Okay, so I'll repeat this figure. Optocoupler is used to isolate the drive circuit with the power circuit. In this figure, only one MOSFET is shown as a power circuit. It's a power MOSFET. So we have to trigger this power MOSFET, and for that purpose we are using this circuitry. If you see this circuit consists of transistor Q2, Q1, Q3, right? And then finally M1. M1 is a power MOSFET. This Q2, Q1, Q3 are the low power transistors. Okay. Now we will see again the operation of this circuit. If input pulse is present, the LED turns on. If input pulse is absent, LED turns off, right? So when LED turns on, it emits the light. This light falls on the base of transistor Q2, right? So transistor Q2 turns on. If transistor Q2 turns on, then it's basically an emitter follower. So current flow through the emitter, right? So voltage will drop across the resistor R1. If this voltage is greater than 0.7, transistor Q1 turns on. Transistor Q1 turns on. Okay. Once transistor Q1 turns on, the voltage at the collector of a transistor Q1 is equal to 0. Ideally 0. Practically VCE saturation. It may be a 0.1 or zero point 0.2 volt. So this voltage is applied to the transistor Q3, and because of this low voltage, transistor Q3 remains off. Transistor Q3 remains off. If transistor Q3 is off, the voltage at the collector of transistor Q3 is equal to the VCC, right? So this voltage is directly applied to the base of or gate of MOSFET, and MOSFET turns on. So actually this MOSFET turns on with the help of this VCC, but it happens when transistor Q2 is on. If Q2 is on, Q1 is on. If Q1 is on, Q3 is off. And if Q3 is off, then the voltage at the collector of Q3 is equal to VCC, which will trigger the transistor M1, right? So the total circuit, that is Q2, RB, R1, Q1, R2, R3, Q3, right? And this RG. This forms a triggering circuit for M1, but the actual triggering circuits which generate the pulses which are isolate from this circuit, and this photo transistor and LED is called as optocoupler circuit. The combination of these two components, the alone LED is not called optocoupler, alone transistor is also not called optocoupler, but if there will be a one LED and one photo transistor or photodiode or light activated SCR, then you can say that it's a optocoupler, right? See, in this particular circuit, if suppose this M1 damage, this M1 gate damage, so definitely what happens, the gate current flow through the Q3, then Q1, then Q2, but all these three transistors may damage due to the large current flow through the gate, but still because of this optocoupler, it means light falls on a base of transistor, only that time transistor turns on. Otherwise, there is a no physical connection between this driver circuit and power circuit. So there is a no physical connection. If no physical connection, if your power devices get damaged, still your driver circuit will work as it is. So your power circuitry, sorry, logic circuitry, which is basically a costly circuitry which generates the triggering pulses, is protected from any kind of hazards, any kind of failure in a power circuit, any device get damaged in a power circuit. So this is another method, and which is very good and precise method. Even it has a very large advantages, that is there is a no physical connection between the driver circuit and power circuit. This is one of the most important advantage. And disadvantage, if you place your LED for long distance, then definitely your Q2 never turns on. If Q2 never turns on, the gating signals will not be applied to the transistor MOSFET M1. So distance between LED and phototransistor should not be far away. Whatever the range is given, one maybe 10 centimeter, 5 centimeter, or less than of that, you should keep the LED very close to the base of transistor. But still, there is a no physical connection, so no any damage uh, occurs in your logic circuit or your gate driver circuit. So these are the two isolation methods. Out of that, optocoupler is good as compared to the pulse transformer, but optocoupler method is basically a complicated, sometimes you can say costly method. And again, the precautions and whatever the care should take, that is again important. So these are the two methods. Out of that, optocoupler method is mostly used by the users for isolation between a triggering circuit and your power circuits. Okay, so this is the isolation. Optocoupler, that theoretical part is given here for your reference. You can read this one. The complete explanation what I explain here, that is given here for your reference. So in PPT, uh, the working of this circuit that is given. So I'll share this PPT with you, so you can read again this explanation. Okay. Now next one is SCR triggering circuits. I think PPT in front of you is still optocoupler isolation method, uh, because of again a low internet problem, internet connection, or maybe a low data rate. It's now difficult. Anyone tell me the slide in front of you? What is which slide shown in front of you? I think the slide has changed now, but still it is not the actual slide.
Synchronize UJT triggering for SCR.
Okay, okay. So it's very good. Synchronize UJT triggering for SCR. So this is the first triggering circuit, and even in our laboratory we have a practical in which the same type of triggering circuit is used. Okay. So before to explain the triggering circuit, I just want to explain you what is UJT, right? Because this UJT may be the not the part of your syllabus in first year as well as in second year, right? So I'll just explain this UGT in a short, and then we will see the actual triggering circuit. Okay. So see, this UGT is called uni-junction transistor. It is looks like JFET or FET, but it is not a JFET. Remember this thing, whatever the terminal name, base 1, base 2, and emitter, right? If you see the JFET, it has a terminal called drain, source, and gate, right? In JFET also, there is a one channel and one P-type semiconductor is sandwich, right? But here, the P-type and N-type, still it is same, but in that particular JFET, the N is heavily doped and P is lightly doped. Here P and N both are heavily doped. So the construction is different than JFET. Definitely the figure shown is very similar to the construction of JFET. Okay, but it is not a JFET. Remember this thing. If you see the symbol of this particular JFET, sorry, UJT, which is again similar, but if you see actual symbol of JFET, if you remember, the terminal connected is a gate which is a straight. But in this particular symbol of UJT, the terminal is called emitter, which is slightly downward direction connected to the channel. Okay, so this is the difference between UJT and FET. The working is very different. Okay, but the construction and symbol is very close to the JFET. So remember, UJT and JFET are the two different components. Okay, two different components. Even in JFET, there is a one PN junction, so that is also called unijunction transistor, but which is basically a voltage control device and this is a current control device. So remember this thing, uh, JFET and UJT is a different, right? As per the construction and symbol, it looks like the same, but it is different. If you see the equivalent circuit of UJT, it is very different, right? At the emitter with the channel, there will be a one diode, PN junction diode, because there is a one PN junction and two resistors. One is called RB1, which is a variable shown in a figure, and RB2 is a large bulk but constant resistance. So total resistance, channel resistance is called as RB1 plus RB2. Okay. So this is the equivalent. Third figure is the equivalent diagram of UJT, and that is again shown in a third one, fourth one. So unijunction transistor has a one PN junction, thus its characteristics is very different from those of BJT and field effect transistor. If you see, unijunction transistors can be represented by a diode of fixed bulk resistor RB2, that is between base 2 and emitter, and variable resistance RB1 between emitter and base 1, and a diffusion resistance RD that is not shown but it's very small. As the emitter current IE increases, see, this is again a current control device and JFET is a voltage control device. Remember this thing. So as emitter current IE increases, the variable resistance RB1 will decrease. If you see the symbol of JFET. I'll again change the slide. I don't know it is visible to you or not, but in particular symbol of unijunction transistor, if you see the terminal which is connected to the channel, that is emitter terminal, it is not a straight connected, it is connected somewhat slightly downward direction. If you see, right? So the as the emitter current IE increases, the variable resistance RB1, because the terminal base 1 and emitter, the resistance between these two terminals is called as RB1, which is shown as a variable resistance. Because as your emitter current, when you apply current to the emitter of this UJT, what happens? The current flows from emitter to base 1, right? So as your current increases, the resistance of that particular RB1, that is resistance between base and emitter, decreases. That is varied. That's why it is shown as a variable in your slide. The total resistance, that is called RBB, that is addition of this RB1 plus RB2. Once UJT is turned on, the diffusion resistance RD will decrease as junction density of holes P type into N type is higher than density of. See what exactly happens in, again the same slide I have shown, that is synchronized UJT triggering for SCR. So if you connect the positive voltage to the emitter with respect to base 1, right? So what happens? The that is shown here in a last figure, that is equivalent circuit diagram. So VBE1, when we increases, then the junction between this P and N repletion layer decreases and junction breaks, and then current start to flow from emitter to base 1 back to the battery. If you see the diagram, that is synchronized UJT triggering circuit. So base current increases, sorry, emitter current increases, then the diode, that is PN junction diode, breaks and current, large current flow through the emitter towards the base, so that the resistance between the emitter and base called as RB1 decreases, right? So this is the characteristics of UJT. Uh, this working of UJT is very similar to the diode. If you see here, this characteristics, shown with this particular red graph. I think it is visible or not, I don't know, the slide is changed or not. So this red line basically shows the characteristics of this UJT, right? I think it is not shown, I don't know exactly. Okay, is it visible that this characteristics of curve of UJT that is shown in front of you? Is it visible to all?
Yes, sir.
Okay, because it is not visible for me, so it means actually, yes, okay, now it is changed. Uh, so in this particular graph, the peak point when the junction breaks and current increases, that current is shown here with the peak point called as a VP. After that, what happens? The resistance decreases, right? Resistance RB1 decreases, and because of that, the reverse current flows for a short time. So your current decreases, right? And sorry, the current that is shown on x-axis and voltage shown on y-axis. So this is a peak voltage when the diode turns on. Once diode turns on, then the voltage decreases up to the valley point and your current increases. After this valley point, the current increases but the voltage remains constant. This is the ideal value called as a VV. This is a voltage across that particular RB1 when the UJT is in on state. This is the voltage across RB1 when UJT is in on state. So this is called valley point. After that, the current increases, but the voltage remains constant, ideally constant, but practically a small current increases. So this particular region is called as a negative resistance region, then saturation region, and this is a cutoff region. Cutoff region from the peak point, right? IP, that is a current, peak current, and VP is a peak voltage. So before the peak point or peak voltage, that region is called as a cutoff region. But at the peak, that is the voltage required to turn on or to break the PN junction, that is called as a peak voltage. So once the diode turns on, see, dear student, that diode, PN junction diode, definitely having voltage rating of 1 or 2 volt, but because of RB1, the current increases up to the IP, and it required maybe a large voltage, and that voltage is called as a VP. Once we reach to the VP, junction breaks, and then current increases through that particular device in reverse direction. So maybe the voltage start to decreases. This region basically called as a negative resistance region, and then it reached to the valley point, and after valley point it remains constant. Okay, so theoretical part for this particular characteristics as shown here, as long as the applied emitter voltage is less than VRB1 plus VPN, this VRB1 is a voltage required to increase the free charge carriers at that RB1, right? So this is definitely a breakdown voltage of a diode plus VRB1. That voltage is required. There is a no emitter current I because the PN junction is not forward bias. The value of emitter voltage which causes the PN junction to become forward bias is called as a peak point voltage or called as a VP. So VP is equal to NVBB plus VPN, right? So that is the voltage required uh, to break the PN junction diode. Directly PN junction diode, we are not applying the voltage. There is a large resistance called as RB1. So emitter current flows through this RB1 and then break the junction, that is PN junction, and then emitter current start to flow. So it requires a large voltage. So VP is the voltage which required to turn on this device. Once device turns on, the voltage across that device is equal to the on state voltage drop, right? After switching, the UJT operates in a negative resistance region up to the emitter current I equal to the valley current called as IV, whereby the device gets saturates. At switch on, the holes is injected into N type, right? The increase of holes